So I am looking at the impacts of permafrost thaw on the methylmercury production in the discontinuous permafrost zone of Western Canada. And so as some of the previous presenters have talked about, rapid climate change in northern ecosystems is likely to result in thawing permafrost. And this threatens to influence some of the mercury dynamics in these systems in a number of ways. This includes mobilizing large stores of previously frozen methylmercury. And the way this works is that as permafrost thaws, the active layer where microbial decay happens deepens. And so it has the opportunity to reach some of the frozen mercury that's been bound to organic matter and then decompose that organic matter and essentially release the mercury. Permafrost thaw is also going to transform elevated peat plateaus, which kind of sit on top of that layer of ice, into thawed bogs and fens. And this was likely to alter the mercury dynamics in these areas because these thawed bogs and fens are areas of high methylmercury production, essentially transforming inorganic mercury into methylmercury. And this is concerning because methylmercury is a neurotoxin and is known to bioaccumulate. So once this mercury gets transformed into methylmercury, it can be transported downstream into rivers and lakes, and then it can bioaccumulate and reach potentially toxic levels in the fish of the region, which then poses a human health risk to anyone consuming those fish. And so although we generally know that peatlands are areas of high methylmercury production, there's still limited research on kind of the mercury and methylmercury dynamics of in different peatland types formed by permafrost thaw. And so here we have preliminary results from this past fall, where we looked at 3 sites in northern Alberta. And so we looked at a bog, a moderate rich fen, and a rich fen. And you can see that on this graph to the left here, although total mercury between these sites are relatively similar, the concentrations of methylmercury and the percent methylmercury that makes up total mercury are quite different between sites. And the percent methylmercury of total mercury matters because this is a measure of the net ability of a peatland to produce methylmercury. So we can see that really the rich fen appears to have the highest production of methylmercury, followed by the moderate rich fen, and then the bog. And within this, there is within peatland variation where we see that areas closer to the center of peatlands tend to produce more methylmercury than areas along the margin. And so this all has implications for the methylmercury concentrations on the landscape, and in particular concerning the downstream concentrations that will end up in fish. And so, but it still needs more research. And so over the next 2 years, this is something that we're planning to look at. And that is investigating the possible mechanisms that are driving these differences that we're seeing, including looking at the microbial community, water chemistry, and organic matter quality, among other things. And then we're also going to use a catchment scale approach where we measure methylmercury in downstream rivers and streams, and relate these back to catchment characteristics, including the degree of permafrost degradation and the land cover of these different peatland types. And so we're hoping that tying all of those together in the future, we'll be able to have a better idea and better predict areas of landscape that are more at risk for elevated methylmercury concentrations, and hopefully be able to identify maybe some areas that we should be monitoring more closely. And yes, with that, I would just like to thank my co-authors and everybody else who contributed to this and will contribute to this in the next couple of years.
Awesome.